Hi guys, BuildZoid here, and so you might be like, why are we looking at the same motherboard twice? And the reason is very simple. I didn't like the previous version of this video, so yet again we are taking a look at the PCB of the MSI Z490 Godlike. Now this is obviously going to be MSI's flagship for the Z490 platform, so expect a price tag north of $700. So, while this is not a motherboard I would recommend most people buy, it is a motherboard that does do a lot of really cool stuff because, well, if the motherboard's going to cost $700, there's no real restrictions on, you know, design. Like, there are still things where it's like it's too expensive to do that, but there's a lot less of those kinds of restrictions on the design of the motherboard where, you know, cost is a limiting factor. So, let's get on with it. Starting off with the rear I/O, this looks a lot better than what you might get on an X570 Godlike, which I'm really happy to see, because apparently my criticism got through, because that board was terrible. Anyway, so rear I/O on this board, we've got 10G Aquantia, that's this chip right over here. Then we have this 2.5 gig, and that's a Realtek chip, and I think that's that chip over there. I'm guessing based on the fact that that's the only Realtek chip I see. There's also two Thunderbolt ports. I think that two, but there are Thunderbolt ports. There might be two of them. I'm not 100% certain. That's taken care of by this chip over here. And then we've got a bunch of USB ports, a PS/2 port, which this is mostly for overclockers because USB ports have, like in certain overclocking scenarios, USB ports cause major problems. So PS/2 doesn't. There's also Wi-Fi 6, and we've got a BIOS flashback button, so you can update the BIOS of this motherboard without even having a CPU installed. That's not really that useful most of the time, but one of the cool things that this can do is if you, for example, have a power outage in the middle of a BIOS flash and it corrupts the BIOS flash process, the BIOS flashback functionality can recover from that sometimes. Not always, but it can recover from that. So it's great for sort of dealing with corrupted BIOS flashes. And then the clear CMOS button on the rear I/O basically means if if you're a normie and you're using a case and then you do some memory overclocking or any kind of overclocking and the system stops posting, you have a clear CMOS button to get you back up and running, and you don't even need to take off the side panel. So that's my preferred location for clear CMOS buttons, because if it's on a test bench, it actually doesn't matter. And if anything, I prefer the clear CMOS button being far away from the power reset. You know, the buttons I'm going to be mashing a lot, I want clear CMOS far away from them, because sometimes, like I think I have one board where there's like safe boot and clear CMOS right next to each other. Not a pleasant experience reaching for safe boot and clearing the BIOS. So yeah, rear mounted clear CMOS is my preferred location for it. Now, you'll notice these holes in the rear I/O shield, which sort of indicates to me that maybe the motherboard would have been better off without the rear I/O shield. Like, just saying, you know what's better than putting little holes into a airflow into a plate, not having the plate at all, because that creates a really big hole, and bigger holes are better for airflow. But anyway, we've got these little vent holes on the rear I/O because there's two fans attached to the VRM heatsink of this motherboard, which is just completely and utterly pointless. But the thing is, it seems to be a trend with a lot of Z490 motherboards in general, because MSI aren't the only ones putting just... Like the thing is, this is one of the motherboards where like the fans are basically on the same level as full cover water blocks for high-end motherboards. It's just completely stupid. Yeah, it's like there's more Z490 boards that are doing this now, and it's just like, why? Why are you putting fans on your mega overkill VRMs? And admittedly, there are some boards that are a lot less overkill in the VRM department than this one, where the fans could, you know, be somewhat justified. But here, like, this barely needs a heatsink. Why are there fans in the rear I/O? But anyway, that's what the holes are for. So, yeah, I really hope that those fans don't actually, like, that the fans are there more for, like, existing and not for actually, like, turning on. Because they're not necessary. Like, why are there fans? I still don't get why there's fans in the rear I/O. Anyway, so moving on from the rear I/O, other overclocking features. Over here, we've got a bunch of voltage read points. These are just connected to the motherboard, so They're not the, like, especially for the core voltage, that's not the most accurate voltage reading you could get, because the most accurate voltage reading for core voltage you can get is from the dye sense. This just measures from the CPU socket of the motherboard, which, you know, is kind of the norm for how this is implemented, so at least it's comparable as a measurement with most other motherboards. But the thing is, socket impedance does vary between motherboards a little bit in my experience, so it's just like not 100% comparable, but still, you know, if you don't want to be running any monitoring software, then this is really, you know, this is good to have for overclockers, and most people don't really use voltage read points anyway these days, so, you know, not really a huge deal in my opinion. Hiding under, like, I'm not sure what to call this, but yeah, hiding under this plastic thing over here, we have the postcode for the motherboard. That's in this area. And then the other part of it is actually a colored OLED screen, which I think is a completely stupid gimmick, but it's a feature that the Godlike series has had for, I think they have it since like Z270 or something. Like they've been putting OLED screens on their high-end motherboards. I've still haven't figured out the point of doing that. But yeah, it's there. Apparently it can do some actual like hardware monitoring, but it's just like, I don't know. Like the postcode already does CPU temperatures. It's like I don't really see the point of all of this, but it's there, you know. So, and it doesn't hurt anything by existing, except the price tag of the motherboard, obviously. But I don't think removing this alone would be enough to make this motherboard significantly cheaper anyway. Over here, we've got 4 sort of basic troubleshooting LEDs. So we've got CPU, DRAM, VGA, and boot. So essentially, these LEDs will just tell you what thing is not working. Unfortunately, they're all the same color, and as you can clearly see, they're also squeezed between two headers and right next to each other. So if one of these lights up, you're probably just going to go look at the postcode instead, because you're not going to be able to tell which one lit up. So yeah, like if they color-coded them, at least you could eventually remember which color corresponds to which problem, and then, you know, it wouldn't be an issue anymore. But as it is, the motherboard has a postcode, so this is made completely redundant, and it doesn't matter that much that, in my opinion, the way this is implemented is terrible. Anyway, so moving along the board towards the bottom, down here we have a bunch more overclocking features that I actually really like. So over here we have a SloMo Jumper. This is for extreme overclockers. It basically allows you to force the CPU to the lowest possible clock speeds. Great for taking screenshots, great for doing like messing around in Windows with liquid nitrogen on the CPU, because the reduced clock speed does actually reduce the power consumption of the CPU. It also means that you're less like installing drivers at 6 gigahertz is not is not necessarily the best idea. So slow mode kind of, you know, gives you a very easy, quick way to drop the CPU clock speeds down and get some extra stability as well as extra power efficiency, because just lowering the clock speed reduces power consumption. Well, it's not really power efficiency, it just reduces the overall power consumption. So, you know, you're going to be burning through less liquid nitrogen, doing things in the operating system. Anyway, next we've got 2 BIOS chips over here with LEDs to indicate which one's active, because there is a dual BIOS switch over here. Also, why is there an LED over there? Like, the BIOS chips are right here, so yeah, but anyway, board has dual BIOS. Dual BIOS is a great feature for, one, if you manage to screw up one of your BIOS chips so bad that the BIOS flashback functionality is no longer capable of, like, recovering it, right? Like, if that's no longer capable of recovering one of your BIOS chips, then you can just not use the bad BIOS chip and go to the backup one. And then the other thing you can do with it is you can very easily do comparisons between various BIOS updates, where you'll put one BIOS version on one BIOS chip, a different BIOS version on the other BIOS chip, and then you can go back and forth between them and do comparisons very, very quickly, because you won't have to actually, like, if you had a single BIOS board, every time you want to test some change between the two BIOSes, well, you need to flash the board, right, which takes time and is just kind of annoying to do. So yeah, dual BIOS is a really, really nice feature to have as an overclocker. Unfortunately, I do believe this is the only Z490 motherboard to have dual BIOS, which I don't know why they're gating such a basic feature behind a 700, like, it's not actually $700, it's at above $700 as a price tag, right? Like, I don't know the actual price, but it's definitely not below $700 as far as I know. At the same time, you might have seen the Z490 motherboard price leaks where this board was listed as being like $1,000. It's not that expensive, but it is not below 700 as far as I know. So anyway, so that's the dual BIOS functionality. We've got a power button, we got a reset button. So the power and reset, well, you know what those do. That's like the same as your case buttons. Then down here, we've got actually cool buttons like the OCRTT and the OCFS1. So OC failset is MSI's version of Safe Boot. Essentially allows you to get into the BIOS without wiping all of your BIOS settings, even if the settings in the BIOS are unstable, because it'll load you up with sort of like last known good settings. At least that's my understanding. It could also do what the Asus boards do, where it loads you into the BIOS with like stock settings, which is actually really cool as well. But I like either implementation of this kind of soft, clear CMOS functionality is really great. Like, I love it. So, though personally I prefer the one where it's just like it goes back to stock settings without wiping your settings. Because that one, like, sometimes the last known good functionality can remember a set of settings that are technically not that unstable, but they're still pretty unstable, right? So, yeah, anyway, better than not having, like, still better than not having safe boot functionality whatsoever. The OC retry button is basically a really hard version of reset. So if you're pushing the CPU really hard, you can actually crash the CPU so hard that the reset and the power button stop working. Now, obviously, if you hold the power button for 10 seconds, that still works, but you can definitely crash a system so hard that the reset button stops working. And for those scenarios, you have the OCRTT button, which the retry button just forces the system to reset no matter what. So it's really convenient if, you know, you lock up the system really hard. It's also great for doing basically memory training, which is if you're running really hard memory settings, the CPU is going to have a hard time sort of figuring out how to run them. And so one of the things you can do is you can just mash the retry button once the CPU gets stuck on the memory training part of the post process. And if you get, like, if the CPU is just about able to do those settings, you know, after some time, like after enough retries, it might figure out a combination of memory settings where it actually manages to run. So yeah, basically you can use this to tell the CPU to try the memory training again, right? That's part of why it's called retry instead of just like hard reset. You know, it's like you can retry your memory training procedure over and over and over again until you lose sanity or the settings work. I guess you could also wear out the button. Then over here we have an LED switch, LED on-off switch, so you can just disable all the LEDs on the motherboard, I assume. And then below that we have a stupidly implemented 6-pin power connector. So the point of the 6-pin power connector is to feed extra power into your PCIe slots, because the 24-pin power connector over here is not designed to handle much more than, I think, 240 watts of 12-volt power. Well, it depends on the version of the 24-pin power connector that you have. But basically, once you start looking at like triple or quadruple GPU setups, there's a very good chance you're going to melt the 12-volt pins of your 24-pin power connector. So the solution to that is to include a 6-pin, you know, an extra power connector to provide extra 12-volt power to the PCIe slots if you're running 3 or 4 GPUs. Now, you may notice a fundamental design flaw here with how the 6-pin is, you know, attached to this motherboard and where it's located, where if you plug 3 GPUs into this motherboard, and they're, you know, your usual 2-slot GPUs, or even single-slot GPUs, there is no way there's no physical way you're getting that 6-pin power connector connected. So, yeah, it's like you can either run 3 GPUs or you can have that 6-pin connected. Therefore, that 6-pin is like self-defeating by design. It's complete, like, I don't get how it's so hard. Like, the funny thing is like MSI makes GPUs. Like, they have to be aware that a right-angled 6-pin connector exists. It's what they use on their GPUs, right? Like, GPUs have right-angled 6-pin connectors. Why can't the motherboard have one of those? I have no idea. The other thing is they could have also stuck it somewhere in this location, right? Like, there's nothing in this area of the motherboard ever, so they could have put it over there. Because the thing is, there's a lot of motherboards that will have the 6-pin in a less stupid location, and that location is right here. And the reasoning for this area. And the reasoning for it being in this area is it's convenient, right? If you have your power connector over here, then you just run it into the 12-volt power plane that looks sort of like that anyway, and so it doesn't take a lot of like design, like layout changes to get the 6-pin in that location and make it functional. However, If you have it right over there, then, you know, let's say you will have a 3 or 4-way GPU setup, you're running a power cable to like the worst location on the entire motherboard. Though, well, okay, one of the, like, just not a convenient location to run a power cable to. But this right here, this is worse, right? This is worse. MSI aren't the only ones to ever, like, misimplement a 6-pin power connector like this for PCIe slot power. Gigabyte has done this on their X570 Aorus Extreme, where it's just like your 6-pin literally makes it like you plug that 6-pin in, it becomes impossible to use the third PCIe slot. Therefore, you can't run, like, you can't use it for its intended use. Dumb. Really, really dumb. And I remember complaining on the X570 Godlike that that board has 4 16x PCIe slots, so you could run 4 GPUs on it, but it doesn't have the power connectors for it. And then here we have a board which, A, doesn't have 4 PCIe slots, so the 6-pin is kind of borderline as to if you would even need it in the first place, but it's also just implemented completely incorrectly. It's just like, I don't know, guys, did you actually think about this? At the same time, multi-GPU setups are very dead, so it's not a huge deal, but it's just really dumb that you'd have like, it's a 700, you know, it's a high-end $700+ motherboard. You would assume they would get something like adding a 6-pin power connector correct, you know, like, but obviously, like, it's not a priority. Nobody runs triple GPU setups anyway. So moving along the bottom edge, we have one last kind of cool feature for overclockers, and that's these two jumpers right over here. These are JLN1 and JLN2, so J and JLN2. And so JLN1 removes cold bugs. So essentially this allows you to run JLN1 will allow you to run the CPU at very low temperatures. JLN2 removes cold boot bugs, which will allow you to boot the CPU at very low temperatures. So I'm going to assume that Comet Lake behaves a lot like Coffee Lake, KB Lake, Sky Lake, where all of these CPUs can technically go all the way to full POW, but they have a problem with it where essentially you need to set a bunch of voltages to very specific levels, which, well, very specific. Some CPU, like, there's a general range that works well for a lot of CPUs, and then there's some CPUs that don't work within that range, and those are really annoying to work with because they make jumpers like this not function the way you'd hope they would. But basically all of these CPUs, they'll go down to minus 120 on completely normal voltage settings. Like, you could literally just, you know, take you can take the lowest end, like Z270, Z370, Z490 motherboards, and you can run them down to minus 120, minus 110 degrees just fine. It's no big deal. But if you want to go below those temperatures, then you need to set a bunch of voltages you need to set a bunch of voltages appropriately. And that's what these two jumpers do for you, because it's a massive time saver. Not having to dial in the voltages yourself. Also, I would assume that these JLN1 and JLN2 work through a clear CMOS. So if you're, you know, like if you're at minus 190 and you screw up your settings and the system stops posting, well, you can clear CMOS, and you're not going to have the problem of not being, like, you're not going to have to pull the CPU back up to minus 110 to post. Because if you have a motherboard without the ability to force the very low temperature voltages, even like, just, you know, have those constantly enabled even through a clear CMOS, then as soon as you clear CMOS, you need to go back up to like minus 110 so that you can go into the BIOS, set the voltages correctly, and then pull down to minus 190 again. And it's just like, that gets really annoying. So yeah, these are really cool features for extreme overclockers. And unfortunately, you know, like, this is the kind of thing that for MSI, because MSI doesn't have an extreme overclocking motherboard lineup, not a, like, proper one in my opinion. Like, this is a Godlike, so it kind of tries to do everything, right? It tries to be a gaming board and a workstation board and an extreme overclocking board, which is how it ends up with functionality like this and a price tag of $700+. Yeah, it's just like, the thing is, it's a shame that it's locked behind such an expensive board, because if you're going to start, you know, if you want to get into LN2 overclocking, you probably don't want to start on a $700 board, because if you're going to kill something, this is going to hurt a lot. And there are you know, like in the past, MSI had the M Power and X Power series where, okay, the X Powers were really expensive, but the M Power boards basically tried to be somewhat stripped down in terms of the feature set and were really geared towards extreme overclocking. So they'd throw out anything that you don't need for LN2. And these days, the only board that really does that is like the Apex series from Asus, and even the Apex boards are kind of, you know, since they've been announced, they've been slowly getting more expensive and slowly trending more towards being gaming boards. But yeah, well, MSI straight up doesn't have an extreme overclocking board line, and I don't count the Godlike series because the Godlike series is just like, well, they just kind of do everything on these, so that doesn't really count. But yeah, you could definitely, like, this is the board that, you know, MSI intends to use for extreme overclocking when they want to show off their LN2 overclocking capabilities. So that's why they include this kind of functionality on the board. But yeah, you know, not very accessible. Like, I would assume most people would get an Apex instead of this if you want to go on LN2. Anyway, so that covers kind of all of the extreme sort of, well, all of the different sort of basic functionality for overclocking and, you know, other basic functionalities as well. Let's talk about the power delivery. So for the VRM here, we are looking at a beast, and unfortunately, it's not a very unique VRM. There's a lot of motherboards on Z490 using this VRM, even in MSI's own lineup. But anyway, this section right here, that's the V-core, and it is a 16-phase, and it's controlled by this chip over here, which that is an ISL 69269. And so the ISL 69269 is a really cool voltage controller because this thing goes up to 12 phases and can do 3 outputs. So here it's running as an 8+1+1. There are actually also boards running the ISL 69269 as a straight 12+0, which we will be looking at some of those in the future. But anyway, MSI is running it as an 8+1+1. The one of the plus ones is this right here, which that's for the iGPU, so that the motherboard is capable of doing quick sync. This was a thing on Z390, and also it's a thing again on Z490. There are motherboards with no iGPU VRMs, so if you want to use the quick sync video encoder that's included in the iGPU of your Intel CPU, so, you know, you get like a 10900K instead of a 10900KF because you want that quick sync functionality. Well, if your motherboard doesn't have an iGPU rail, you don't get quick sync functionality because the iGPU literally can't turn on because there's nothing to turn it on with. So anyway, the Godlike does have an iGPU rail, and that's one of the plus ones. And then down here we have the VCCSA rail, which is the other plus one. So that's the system agent power, and that's it's kind of the like interconnect between the cores, the PCIe, and the memory controller, and everything like that. So yeah, anyway, let's talk about the V-Core VRM. So it is a 16-phase. Obviously, to go from the 8 phases of the ISL 69269, the motherboard has to use a bunch of doublers. So we do find those on the back of the board. That's all of these little chips. And those are all ISL 6617s. While we're on the back of the board, I also forgot to mention there's a hole in the CPU socket. This is for putting through K-type thermocouples for extreme overclockers so that you can monitor the CPU temperature with basically you can like glue a thermocouple to the back of the CPU and measure the temperature of the CPU that way, because when you go below 0, the CPU's built-in temperature sensor breaks, and normally the only other way you can monitor the temperature of the CPU is through the thermocouple in your LN2 pot, but the LN2 pot temperature, like, that depends on how good, like, the accuracy of that thermocouple's temperature reading really depends on like how well your thermal paste is behaving. So to sort of work around all of that, you can just attach a thermocouple to the back of the CPU, which again isn't going to give you like, you know, silicon level temperatures, but it's going to give you a temperature that isn't affected, like that would show issues like, say, the thermal paste being bad thermal paste contact and those kind of, you know, issues that you might run into when going sub-zero. You know, like sometimes the thermal paste fails, and sometimes it's something as stupid as you got blue shop towel between the LN2 pot and the CPU IHS, and it's like, and you'll be wondering like, why is it running so hot? My thermal paste was fine. Well, no, your LN2 pot temperature will be really low, but the CPU will be really, really hot, and you'll be sitting there like, I wonder why that is. So with something like this, you can catch those kinds of issues a lot sooner. Anyway, because because the thing is, at idle, if you have bad thermal contact, like if you have bad thermal paste contact at idle, the CPU will actually still be well below 0, and then when you load it up, suddenly the temperature jumps up out of nowhere, and it's just like, what? How did that happen? So yeah, also the temperature sensors can actually, like, you can glitch them out with the various voltage settings. So yeah, it's just better to have a, you know, known good K-type thermocouple attached to the back of the CPU. So to get another indication of the operating temperatures. Anyway, so back to the VRM. There's doublers on the back of the board. The doublers, actually, we should just stay on the back of the board. The ISL 6617s are basically the most advanced doublers you can get that I'm aware of, at least. Though that's more because they're kind of compensating for, like, there's different ways to implement doublers depending on which manufacturer you're looking at. So like International Rectifier's approach is that the doubler is actually really dumb and the controller has to do a lot more work to sort of get around that. Intersil's approach is the ISL 6617s can actually do current balancing. They can do they can also run both interleave and run synchronous mode. So they actually also do the current monitoring, and then they sum up the currents and like send that back to the controller. So these have a lot of these are basically really smart doublers. But that's just sort of to potentially simplify the requirements for the actual controller. Anyway, so depending on how MSI is running them, so synchronous mode is meant to be a transient response optimization so that you can potentially turn on all of the phases at the same time. If you're in interleaving mode, there's just no way to do that because the interleaving mode only interleaves every other PWM pulse gets sent to a different phase. So if you want to send a high pulse to all of the phases at the same time, there's no way to do that in the interleaving mode. So with synchronous mode, essentially the controller can go like, oh, I want to temporarily boost the transient response capabilities of the VRM. It sends a synchronous, like it changes the voltage level at a pin on the 6617, and the 6617 temporarily goes from interleaving and going from one phase to two phase operation. It goes back to like single phase, and your VRM temporarily goes from being a 16 to being an 8 phase. There are a lot of motherboards which will actually have the ISL 6617s forced into synchronous mode all the time. But even in permanent synchronous mode, these actually do offer a small efficiency increase compared to just putting stuff in parallel, because they can still current balance even in synchronous mode, which is kind of neat. That's kind of what's going on with these. Ultimately, I am like, the main concern with the use of doublers in a VRM is that they can add delay to the PWM signals going from the controller to the power stages, which can lead to slower transient response. Basically it slows down the transient response of the VRM. However, that delay is very, very small, and there's plenty of ways to work around it. As far as I can tell, there has to be plenty of ways to work around it, because on Z390, the best transient, like the motherboard that had the best transient response in my testing was a EVGA Z390 Dark, and that uses a bunch of ISL 6617s in its 12-phase VRM as well. So obviously, the delay exists. The delay is not that much of an actual issue. And especially with what MSI is doing on the output filtering of this motherboard, I expect the transient response of this board right here to be absolutely incredible. But we'll get to that in a little bit. So the control scheme here, we're doing an 8-phase to 16-phase through doublers. I don't really I don't see anything really wrong with that. And now let's talk about the actual power stages. So for the power stages, we're looking at a bunch of ISL 99390s. These are 90 amp smart power stages. Now, you might be thinking that these have to be like way better than the 70 amp smart power stages that we've seen in the past on other motherboards. Not really. Surprisingly enough, these actually aren't massively better. Like they're comparable in terms of performance. Unfortunately, the data sheets don't line up in terms of the operating parameters perfectly, so these are rated at slightly higher switching frequencies than the International Rectifier 70 amp smart power stages, so you can account some of the heat dissipation difference down to that. But yeah, these like, these don't really give you some huge significant advantage over the 70 amps smart power stage parts. However, they are a hell of a lot better than a lot of the like 50, 60, 55, 45, 40 amp power stages that you would see on, cheaper boards. So with these 90 amp, also, so that's kind of about the current rating. Like, actually, I personally, like, I've come to the conclusion that I don't really like the fact that we have these sort of, like, these are basically peak current ratings for the various power stages. And, like, the thing is, a single ISL 99390 in a very specific cooling environment can do 90 amps continuous output current at 1.2 volts. That's not an issue. It can do that. The problem is if you put several of them in parallel, it can't do 90 anymore. Like, if you have, a bunch of them in a VRM together, no, you're not doing 90 amps through any of these. So I personally would really prefer if we had a standard that was like, like current at peak efficiency rather than like absolute maximum current rating, right? Because the absolute maximum current rating is just like, it's not like you wouldn't actually want to run those power stages in that scenario because they produce way too much heat for any practical, multi-phase designs. So anyway, don't pay attention to, like, basically what I'm trying to say is don't pay too much attention to the 90 amp figure because it honestly doesn't matter that much. Now, and also, unfortunately, I don't think the data sheet for these is public yet, but I have my sources. So, that, like, I've seen the efficiency curves, so, like, I just can't show them. Anyway, for the smart power stages part, so this is also cool, is smart power stages are called smart power stages because they integrate a whole bunch of smart functionality, like temperature monitoring and very accurate current monitoring and overcurrent protection and over temperature protection, and I think also short circuit protection. Like, they have a bunch of protection features, a bunch of monitoring features, which is what makes them smart compared to, more basic power stages, especially like if you go all the way down to like a DR MOS component. Those are a driver and two MOSFETs, and it's just like there's no, like, if you want to measure the temperature of one of those, you need to implement your own external temperature monitoring circuit. These integrate all of that functionality, which, simplifies the VRM design somewhat. Also, these are way more expensive, but so the fact that the VRM is easier to design is kind of a trade-off where the VRM is overall more expensive anyway, so that's not a huge win. But yeah, like these are really, really advanced power stages. It's just that the 90 amp part is just like not actually that useful as a performance indicator. Anyway, so let's talk efficiency. So this VRM outputting 1.2 volts, operating at 500 kilohertz switching frequency, which is just the switching frequency that the 99390 data sheet is spec'd at. You're going to be well, actually, no, these are 99390s. Yeah, so these are going to run on 5 volts. There's a 9930B, or actually, is it the I can't remember now. There's a 3.3 volt variant, but they have the same efficiency curve, so we're actually just not going to mention the drive voltage because it doesn't matter. Because it depends, like, well, it does matter, but it depends on which SKU is being used, and ultimately doesn't actually matter that much because both SKUs perform the same. I assume it's just a cost difference for the lower voltage parts. Anyway, so let's talk current. So the thing is, with a VRM like this, talking about anything less than 200 amps output current is just kind of silly because a modern voltage controller, which, I say modern, but this has been a feature for like at least more than 10 years now. Like, the ability to drop phases out of a multi-phase VRM is just kind of not, like, it's not new. So calling it modern is kind of like, it was modern maybe 15 years ago. Now it's kind of like that's the norm if you're buying a high-end controller. But anyway, high-end controllers as a efficiency optimization will turn off excess phases if you're running at low currents because it costs energy to just switch a MOSFET on and off. And so if you have, so basically the trade-off that you have at low current outputs is spreading the current across more phases has to reduce the heat, like has to reduce, like the decrease in heat dissipation due to spreading the current across more phases has to be greater than the increase in energy consumed, because now you're running an extra set of MOSFETs, right, in whichever phase you added on. So for a VRM like this, talking about currents below 200 amps, you're going to be, like, if you want to actually have decent efficiency, like, the VRM is going to be very, like, shutting down partially. Like at 100 amps, you'd probably need, like, half of this instead of all of it. So anyway, yeah, 200 amps output, you're going to be looking at this VRM producing about 15 watts of heat. And that's, all 16 phases running. I'm not going to calculate below 200 amps because you wouldn't run all 16 phases in those scenarios. Going up to 300 amps, this VRM would produce about 23 watts of heat, which, like, 15 watts of heat spread across 16 power stages. Also, you need to consider this is a motherboard with an 8-layer PCB. Like, at 200 amps output, this VRM doesn't need a heatsink, like, at all. Admittedly, it'll run cooler with a heatsink, but the heatsink is not a requirement for the operation of this VRM whatsoever. And then going up to 300 amps, 23 watts of heat, like, you should still be able to get away without a heatsink. But at this point, the heatsink might actually start being useful. Going up to 400 amps output current, the VRM will produce about 34 watts of heat, and now the heatsink is a requirement, and we'll get to where, the current is actually useful later. 500 amps output, the VRM is going to produce about 48 watts of heat. Very much need a heatsink at that point, and 600 amps of output current, you're going to be looking at about 66 watts of heat. So, yeah, like, you basically need heat sinks from, like, here to here, and below that you don't need heat sinks. Now, theoretically, a 10900K, being a 10 core on the 14 nanometer process, if you're going to max that CPU out, I would expect the current draw to be anywhere between sort of like 200 and 250 amps. 250 amps being very difficult to cool, but theoretically doable. 200 amps, on the other hand, should not be that much of a challenge to cool, considering Intel's, kind of gone out of their way to try improve the thermal performance of their K SKUs for the 10 series. But because of that, this VRM is just kind of like, you could run a 10900K in Prime 95 with AVX, with very high voltages, on this VRM with no heatsink, because you would be in this... Like, you'd be in this current draw range. Yeah, like, the cool thing is MSI does have this VRM on some of their other motherboards, including the Z490 Unify, if I remember correctly. And I will actually be getting a review sample of the Z490 Unify, so that is a test I plan to do. Is like, I very much want to run a Unify with no VRM heatsinks and see if it overheats, because I'm assuming it won't. Like, I'll be very surprised if it overheats. Cause like, actually there was a similar there's a video actually for the 9900K, from Gigabyte, where they're running a 9900K on a 16 phase VRM using 70 amp smart power stages with no heat sinks. And the VRM is sitting at like 70 degrees. And that was after like 24 hours of Prime 95 with AVX, and the chip is doing like 5.1 gigahertz. And yeah, with VRMs in this class, you could say their power handling capability is godlike. Anyway, so yeah, this is absolutely insane level, like, mega overkill. And that's especially why it's like, why do we need the freaking fans in the VRM, right? Like, this is totally unnecessary. Anyway, so power handling wise, crazy mega overkill VRM as you would expect of a Godlike series board. Like, MSI's been doing this for a while. The biggest difference here compared to like some previous Godlikes is I think this might have 2 phases more than some of the predecessors, and it has 20 amp higher rated smart power stages, which actually, in terms of the real world performance of said power stages, doesn't make that much of a difference compared to like the 70 amp smart power stages from International Rectifier. So yeah, because the peak current rating is not, like, at useful current outputs, that doesn't matter that much. Like, admittedly, like, a 40 amp power stage probably sucks even at 20 amps output, but when you're looking at 90 amp smart power stages, comparing them to like 70 amp smart power stages, and looking at the 10 to 20 amp current range, not much of a difference. Or even the 10 to 60 amp current range, still not much of a difference. Anyway, so yeah, big fan of the power delivery here in terms of power handling capacity, and then I'm also a huge fan of what MSI is doing with the capacitor configuration. So these right here, contrary to popular belief, are not MOSFETs. I know, it's mind-blowing, and you might be like, Buildzoid, why are you saying? So here's the thing. I keep getting messages from people who've, like, glued heat sinks to their freaking capacitors on, like, their GPU or their motherboard. And then they try to remove the heat sinks, rip the capacitors off of the GPU. Usually it's the rip capacitors off of the GPU. And I get a message from those people where it's like, I ripped a MOSFET off of my GPU, and my initial reaction is, how the hell did you achieve that? And then they send me a picture of it, and I'm like, that's not even a MOSFET. You ripped off a capacitor. So yes, these are capacitors, as you know, as similar as they may be to MOSFETs, or you know, like, have you noticed how, like, fan control chips are very similar to, well, damn it, MSI doesn't have any of those big, large linear regulators. Like, oh, whatever. Anyway, so these are capacitors, and these are really, really cool because they're SMD aluminum polymer capacitors. And the reason why these are really, really cool is because they have extremely low ESRs and extremely low ESLs, which basically means they're great for your VRM's transient response. So yeah, unfortunately, they're also extremely expensive. You know, looking at like 10 times the cost of your standard generic through-hole capacitors for a given amount of capacitance. And that's part of the reason why the only motherboard in MSI's lineup that uses these is the $700+ Z490 Godlike. And I really hope that I get a review sample of this board, because it would be really, like, I think it would be a really cool comparison to test the transient response of this VRM versus the VRM on the Unify, because again, if I remember correctly, the Unify uses the exact same voltage controller, doublers, and power stages, but the biggest change is that they go away from these very expensive SMD polymer, you know, SMD aluminum polymers, and go with the much cheaper through-hole aluminum polymers, which yeah, I really wonder how, like, that might actually show up in oscilloscope shots in terms of the transient response of the VRM. So I'm very interested in, you know, like, I think that would be a really cool test to do, having two motherboards where, like, the biggest difference in the VRM design, admittedly, this is an 8-layer, whereas the Unify is a 6, but where the biggest difference in the VRM design is, like, the capacitor configuration. Like, I'd be very interested in doing that testing. But yeah, these are great for transient response, and I would not be surprised if this was one of the best motherboards for Z490 in terms of transient response, because it uses all of the, you know, because it's using these capacitors. So, yeah, what else is there? I guess we can talk about sort of this area. Oh, right. iGPU VRM uses the same ISL 99390 90 amp smart power stage. No surprises there. You know, I don't think most people are going to overclock their iGPU, even if they're using it for quick. I wonder if QuickSync scales with overclocked iGPUs. Like, I wonder about that. Somebody should test that. Actually, I guess I could test that if, yeah, I guess I could test that. So I might test that. Anyway, yeah, 90 amp smart power stage, so, you know, no problem powering a iGPU. Though, the funny thing is, iGPUs can get surprisingly power hungry when you overclock them, because normally they're run at, like, very mild voltages, and then once you know, crank up the voltages and clock speeds, like, it's very easy to double or quadruple the power consumption of something that's run at very low stock voltages, right? So, yeah, but still, it's a 90 amp smart power stage. I doubt the iGPU is going to be able to, you know, overload even a single phase of those. Then for the system agent, we're just looking at a pair of discrete MOSFETs. So you have a high side and a low side MOSFET. Nothing special there. The system agent, like the system agent rail of the CPU doesn't really pull that much current. So yeah, like, it's not surprising that MSI isn't bothering with a smart power stage there. Anyway, then down in this area, we have a bunch of, like, well, this area is a mess. Like, this is a regulator, I'm guessing. Yeah, that's a regulator. That has to be, because we've got our inductor, our output filtering capacitors, and then this looks like it might be the actual MOSFETs and control logic, as well as the driver, and then we have that again. Then we have two more regulators like that. These are slightly larger. But basically down here in this area, we're going to have the VCCIO rails, and then we're going to have all of the various sort of extreme overclocking voltages like VCC PLL, VCC PLLOC, VCC VTT, VCCST. Like, there's a bunch of them. I don't really remember them. That's why I'm a huge fan of the JLN1 and JLN2 headers, right? Like, that's the other thing is, like, too many voltages if you need to keep track of all of them. Anyway, so yeah, those are going to be down here, and it's actually like it's kind of neat that MSI seems to be actually using buck converters for all of them, though there are some motherboards that, because a lot of motherboards will actually just use linear regulators to do those voltages for convenience. And I don't like, the thing is, linear regulators technically give you better voltage regulation. The downside is they're far less efficient. So yeah, it's an interesting design decision that MSI is actually going with little buck converters down here instead of just having an array of linear regulators like you'd see on an Asus or a Gigabyte board. Because, yeah, like this might be ever so slightly more efficient, but those rails don't pull a lot of current, so it's just like, yeah, this seems kind of overkill, but hey, if it works, it works, you know, it's fine. So let's talk about the memory. So for the memory power delivery, we're looking at a two-phase, well, we're looking at half of the two-phase because unfortunately it's covered up by this stupid plastic thing. Yeah, two-phase memory power has been standard on, you know, the Godlike series motherboards for a very long time. It's not really noteworthy in my opinion. DDR4 doesn't really pull that much power. You can, like, some of the best memory overclocking motherboards are ITX boards with single-phase memory VRMs. So, you know, having two-phase memory power is, like, it's nice, and it definitely doesn't hurt anything, but I'd be very surprised. Like, I've never actually seen it have a noticeable impact on memory overclocking. Generally, the far more important thing is what, like with DDR4, it's less about how you power the DDR4 and far more about what you do between the DIMM slots and the CPU socket, by which I mean all of the lovely memory traces here. And so MSI is doing something that I think might be unique to them for the Z490 generation, where they're using these weird-looking traces that we can't see because there's not enough pixels in this photo, though there's a lot of pixels in this photo, like much better than some of the stuff I've dealt with, like other, you know, like, say my own photos are terrible. I mostly because I have, like, I can take close-ups of anything that I want to do. Anyway, but these are called tabbed traces. And the idea behind these is that they improve signal integrity for high-frequency signals by reducing crosstalk, far-end crosstalk. Now, if you have no idea what that is, what that means, I can't help you very much because the paper I tried to read, like, there's a paper that I'll leave in the description, but that paper is just over my head, and like I understand the gist of it, but I'm not capable of explaining this to people in a way that makes sense. But the idea basically is that if you have traces running close to each other, which you just have with memory, because there's a bunch, like, memory controllers are 64-bit wide memory interfaces, right? Like each channel is 64-bit, is a 64-bit wide memory channel. So the problem with having all of the traces running next to each other is that they will actually have, like, one trace will interfere with the signals on other traces, and that's called crosstalk. And so by some, you know, electrical engineering magic, adding little tabs to the traces, where you essentially have, like, if you have two traces like this, and you'll have little tabs like that. Well, okay, not like that. Something like this between them. And by having these, and the tabs don't connect the traces, like they're just kind of there. And the existence of these tabs leads to less crosstalk, and that leads to better signal integrity. And better signal integrity means better memory overclocking, because, or at least that better memory overclocking, assuming the BIOS and the CPU can deal with it. Like, there's like, one thing you need to consider is, like, having a motherboard that's capable, like a memory layout on a motherboard that's capable of carrying a 6 gigahertz signal does not necessarily mean that the BIOS is capable of configuring the CPU to, you know, deal with that 6 gigahertz signal. So there's more to it than just having the world's best memory trace layout, but definitely, you know, if you also have the BIOS to work with the trace, like, if the board, like, a bad BIOS will screw over memory overclocking. A bad trace layout will also screw over memory overclocking. So both have to be really, really good. And yeah, I find it really, like, this seems to be unique to MSI, and I wonder how much of a, like if we'll see like a major difference in terms of memory overclocking behavior between the MSI motherboards that use this tab traces design compared to some of the other motherboards out there. At the same time, it's not necessarily fair to attribute all of the memory overclocking differences to the tab traces. Like some of it'll be just BIOS configuration stuff. So, that's one thing to consider. But yeah, so we've got these tabbed memory traces, which I think are really cool, even though I don't really understand the science behind them. They're still really cool because I've never seen these used on any other motherboards before. And they sound like they should actually help, at least within my limited understanding. So the actual sort of basic topology that we're looking at in terms of the memory over here is a daisy chain. And we are looking at an 8-layer PCB, which I mentioned earlier. And MSI claims the following things are possible. So you can run one rank and one rank at 5,000 mega transfers per second. Though if you go to G.Skill's own website, they're going to label their 5,000 mega transfer per second memory kit 5,000 megahertz. So, like I personally just don't care anymore which one you use, even if one of them is technically incorrect. So two single rank sticks in the appropriate memory channels, because it's a daisy chain. So the way daisy chains work is they go to this memory stick, like this slot first, and then they go to the next slot. And then for the other channel, they go to this slot, and then, you go like this. You go from, like, you connect to the, actually, yeah, I'll just draw it out. So you go from the CPU, and then you connect to this slot, and then to that slot, and then for the other channel, you connect to this slot, and then to that slot. And so with every daisy chain topology, you should always use these two memory slots, because, well, there is a really weird daisy chain topology that was used like many, many years ago that doesn't work like this, but modern daisy chains, you always use these two memory slots, because because if you use this memory slot, you have a termination problem where there's a bunch of wire just hanging off of the end of your memory trace, and that's bad for signal integrity. Again, for reasons that I'm not going to try to explain because I'll do a terrible job of it. But yeah, so one rank configured like single rank sticks configured like this. If you're going to run dual rank sticks, so two ranks like that. So, like 32 gig DIMMs or 16 gig DIMMs tend to be dual rank these days. You're going to be looking at 4,400 megahertz. I mean, mega transfer, who cares? Just 4,400. Then if you run two single rank sticks, and this is really surprising because daisy chains don't normally deal well with having every single DIMM slot populated because there's a timing difference between the different memory slots. However, the BIOS and the memory controller the BIOS can be tuned to work around that to some extent. And I guess MSI has done a great job of that because they claim support for 4,400 megahertz on one rank. We will be testing that. If I get the chance to test this board, I will be testing that because those are big claims. Those are very big claims. And then for two rank DIMMs, on all four slots. So if you're going for like 128 gigs of RAM, MSI claims that this board can go up to 4,000 megahertz, which is still, a pretty, that's a big claim. Because I've heard, like, there are people who, I've never tested memory configurations like that. Though what I want to test, what I will be testing if I'll definitely test it on some Z490 boards. If I get this one, I want to test it on this one as well. Is one, I'm not sure how the order works out because sometimes it works better this way. But this is something you can do. Like, you can run triple rank. If you want to be weird with your memory, you can do that. And yeah, I want to test that because that's a really strange memory configuration, and I just think it's cool that it works, and it can actually overclock okay-ish. It's very specific about the order that you put your memory sticks in, though. So yeah, that'll be interesting. So yeah, MSI has big claims for what their 8-layer tab daisy chain memory layout can do. At the same time, in my past experience, MSI has been pretty good about not claiming memory speeds that are very difficult on their motherboards. Like, on Z390, the ITX that I tested from them, they claim 4800 megahertz support, and it does 4800 really easy, except for the part where my CPU's memory controller needs like 1.5 volt system agent for that. So not actually going to run that, but sure. Like the board posts, which is a lot more than you could say for some other boards, where it's like if you tried to go up to 4800, you know, even no amount of system agent voltage is going to say get other some of the other boards to do that high frequencies. So yeah, I'm inclined to believe MSI when they say they can do 4000. These, I don't know. We'll see. I hope I get a chance to test the board. Also, a neat feature for those of you who don't, well, if you're, like, neat feature for people who probably don't watch this YouTube channel. There's a little LED on the board to indicate if your XMP profile is enabled or not. So yeah, if, you know, so basically it's to remind you that if you bought memory with a XMP profile, it reminds you to enable it, because you can just look at the board, and if the LED is not glowing, well, you should go enable your XMP in the BIOS. So yeah, that is it for the Z490 Godlike, and I have to say I like this take a lot better. It's also 54 minutes long. I guess we know what the problem with the previous take was. It was just too short. But yeah, this is an absolute beast of a motherboard. You know, oh, and I guess I forgot to mention that this thing does technically, like once 11th gen CPUs come out, this motherboard should be able to run PCIe Gen 4, because it has the PCIe 4.0 switches, it's got your PCIe 4.0 redrivers, it's also got the more expensive low loss PCB substrate. Again, to just, you know, maintain, like, that's done so that you have better signal integrity over long distances for very high frequency signals, which I've been told it doesn't do anything for memory, but PCIe is, like, actually, PCIe, I think, has a higher giga transfers per second, and actually a higher operating frequency than RAM, which is kind of ridiculous to think about, considering how difficult it is to run RAM at high speeds. But yeah, so you need the like the more expensive substrate, and then the more like the actually, you know, PCIe 4.0 compatible switches and redrivers for that, which also cost more to make that functional. So yeah, and I guess somebody also, I saw somebody ask about the PCIe lane distribution, and so obviously these are Intel CPUs. You've got 16 lanes on the CPU, or for 10th gen this is true. I'm not sure about 11th gen. I don't like, the thing is, buying a Z490 motherboard to then put a 11th gen CPU in it, to me seems like a pretty bad purchasing decision, because like, why don't you just wait until 11th gen actually launches, right? Like, by then you might also get less ridiculously priced motherboards. So, anyway, but with 10th gen, you're going to be looking at either 1604, or you're going to be looking at 884, because this last PCIe slot is hooked up to the chipset. So, yeah. That is the Z490. Oh, and I guess I could have talked about the dual 8-pins. I don't like talking about 8-pin power connectors. Screw it. You don't need both of them. You can plug in one. You'll be fine. There. That is actually it for the MSI Z490 Godlike motherboard. Power delivery, I'd say very godlike. Memory looks to be very godlike as well. Price tag, extremely godlike. What a stupid motherboard name. But yeah, this is not a motherboard I would recommend most people buy, but it is a motherboard, like, MSI is basically showing off what they can do if you give them an unlimited budget. That's why it's so that's why it's going to be so freaking expensive. And it's also why I think this motherboard is really, really cool. At the same time, it's one of those boards that if I wasn't a reviewer, there's no way I'd be touching this. Like, there's no way I'd get my hands on this thing, because I'm not spending $700+ for a Z490 board. Like, even a really cool Z490 board, yeah, no thanks. I'm not interested in that. But yeah, at the same time, I feel like I'm kind of like, if the ridiculous motherboards don't sell, eventually the motherboard vendors will stop making them. Though, considering that we've like, X570 was a price hike, Z490 is another motherboard price hike. I'm assuming high-end motherboard sales are doing just fine, even as much as I don't like the price tags myself. So, because otherwise, why would they keep raising prices, right? Anyway, like, yeah, that's it. That's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. And both of those, both the Patreon and the Teespring store, help out immensely with running the channel. So if you could check those out, that would be amazing. Yeah, that's it for the video. Thanks for watching, and goodbye.